my name is Jonathan Garova. This is Felipe Arturo, Jonathan McGrath, Mike Van Glan, and Bennett Simani. And we represent the D1 team on their Professor Denda. The project scope title is Flapping Wings and Flying Robots. The scope of the project is to design and produce a fully functional MAE class ornithopter. And basically what an ornithopter does is, instead of a traditional fixed-wing aircraft that uses a propeller to reduce thrust, the wings will move and produce thrust. As you can see in the design, right over here, there are 4 wings that flap symmetrically about each other. And this type of mechanism will produce the thrust and lift that the aircraft needs to get going. Our main constraints with building this aircraft is in the wings. The way that insects usually fly is they'll have say a ball and socket joint, and they are able to actively move. They are able to actively move their wings in order to scoop and flap up and down. With this design here, so you can see here, elevator. There you go, elevator up, down, up. So as you can see here, the ornithopter is what is called 3-channel. So its main controls are elevator, rudder, and throttle. So the rudder produces the yawing motion, yawing the aircraft left and right about its center of gravity, and the elevator introduces a pitching motion, which is able to pitch the aircraft down or pitch up while it is in flight. The flapping mechanism produces both the lift and the thrust. And the main issue that we had in terms of designing was being able to passively get the thrust and lift that we needed to fly, because we only have one channel in terms of the flapping channel and only one axis, so it can't scoop actively. So the way that it would have to produce thrust is the wings would have to deform on their own to scoop ahead while they produce lift. So that was our main constraint, and the spars in the front and the stringers in the back had to be a certain thickness that would allow this proper deformation. For our project, this was mostly testing, so we left a lot of things variable in terms of different wing sizes, different spar sizes, all these things, and we're testing. And if you want to talk about the gearbox, John, or? It's good. Here.
That's our design.
So right now with this aircraft it has enough power to just sustain flight. The reason being is our weight constraints were not exactly met. We originally budgeted for a 3.5 gram model, around 3.5 grams. But most of our weight addition came from the gearbox. Traditionally with smaller aircraft, a lot of RC hobbyists, RC modelers will build their own gearboxes and make them out of carbon fiber construction or aircraft plywood and make them as light as they could be. The issue we had with that is we didn't have the tools to do so in terms of the tolerances that had to have been met to put these gears together so that the meshing was correct. So we were able to find a gearbox that was sold by a company in, I believe, Sweden called Didal. And this company makes a lot of pager motors and gearboxes and all these things for small MAVs, for the traditional hobbyists that would want to divulge themselves into a very small class of MAV. So we were able to get a hold of this gearbox and put it in, and it does have its advantages. One advantage is it introduces, it takes away one variable in terms of something that may not work or something that may give us an issue. And two, it's very durable. It's made out of ABS plastic, and the way it was machined by the company, it's very reliable, and you would always have proper meshing in that gearbox. The issue with it is I believe the gearbox was about 1.1 grams. Usually, though, if you make the gearbox properly yourself, they will be a lot lighter. So that is our issue with the aircraft. But to sum it up, the aircraft does fly, and we would be able to get more controlled flight and a longer flight time if it was a little bit lighter. So the next goal would be just to, or for next team or for us, would be to get the aircraft lighter and keep a very similar design in terms of the geometrical properties, so that it will have enough lift to pick itself up. So that's it. Thank you.
Yep, that's pretty much it.
Do you have anything else to say about the display of these cars?
These are the old wings. We had to change it because we were trying to get better deflection on the wings. So as you can see here, these wings are corrugated, like a wrinkle. We did before, we glued the mylar on top of the carbon fiber skeleton, but we decided we wanted to change that. So instead of in the second prototype of the wings, we didn't do the wrinkling. So as you can see, there's more tension. We actually made it smaller, so the wings are smaller. They're better tension. It just proved to be an improvement, and it helped the project fly a little bit more and get more lift.
We'll be back.
Yes, sir.
Right. How about this film you're using?
Mylar.
Yeah. Did you make this, or did you actually purchase?
Purchase.
Yeah. And then what is this one?
Oh no, this is just all the different gears that we have.
Oh, the gears. Yeah. And then batteries.
Yeah, these are the batteries that we have. This is just the skeleton of a wing without the fingers. The spar bar. Over here we have the linkages.
Yeah.
Which is a very important part of the design, because the linkages length have to be just perfect to avoid the jerking motion of the wings. That means when the wing stops flapping, it goes to a complete stop, and then it starts flapping again. If the linkage is too small or too big, it's going to affect the gearbox, and it's going to reduce the throttle and the lift.
Did you manufacture this one?
Yeah, we did manufacture both of them. We used it using a wire inside a carbon fiber tube, and then these actually are guitar strings that
Guitar string.
yeah, guitar strings. So we just put it inside the carbon fiber tube, and we bend the end to make this kind of hook, and over here it's just the guitar string. And then we use rubber stoppers at the end to keep it together.
Good. Thank you.
Yep.